A star just died, and we watched it happen in real time. Not days after, not weeks after, when every textbook says you're supposed to find these things. Hours after. We had never done that before, ever. And what we saw inside that explosion, the actual shape of it, has forced astrophysicists to go back and rethink some of their most fundamental assumptions about how stars die. This is the story of SN 2024 GGI, and it starts with a problem nobody could solve. For decades, where astronomers have known that massive stars end their lives in one of the most violent events in the universe, a core collapse supernova. A star 10, 20, sometimes 50 times the mass of our sun burns through its fuel for millions of years. Then, in less than a second, its iron core implodes, collapses to a ball roughly the size of a city, and a shockwave tears the entire star apart from the inside out. The energy released in that single moment is greater than the sun will produce across its entire 10 billion year lifetime. We've known the broad outline of this process for a long time, but we have never been able to agree on what has driven some of the sharpest arguments in modern astrophysics is what actually powers the explosion. What revives the shockwave? What turns a collapsing core into a catastrophic detonation? Because here's the thing, nobody tells you the shockwave always stalls. Every simulation, every model, every time the shockwave forms, travels outward and then stops. And it runs out of energy before it can escape the star. And yet, obviously, stars do explode. We see supernovae in galaxies all across the universe. So something is restarting that stalled shockwave. Something is finishing the job. Scientists have been arguing about what that something is for over 30 years. And then, on April 11th, 2024, a robotic telescope in Hawaii changed everything. The Atlas Sky Survey doesn't sleep. Every clear night, it scans the entire visible sky automatically, mechanically, relentlessly, looking for anything that changed since the night before. A new light, a brightening star, anything that shouldn't be there. On that April night, it found one. In a galaxy called NGC 3621, located 23.8 million light-years away, that's roughly 140 quintillion miles, a star had just started to die. The light from the explosion had just reached Earth. And Atlas caught it within hours of the first photons arriving. This is almost impossible to overstate how rare that is. Supernovae are completely unpredictable. You cannot watch a star and know it's about to explode. There are no reliable warning signs visible from Earth, and the most scientifically valuable part of the explosion, the very first hours when the shock wave is just breaking through the star's outer surface, lasts for such a short window that even if you're watching, you'll almost certainly miss it. The star's outer shell gets torn away almost immediately. The original geometry, the true shape of the explosion in its rawest, most uncontaminated state, gets buried under cascading layers of debris within hours. By the time most supernovae are discovered, that information is gone forever. Atlas caught SN 2024 GGI before that window closed. Astronomer Yi Yang and her team knew exactly how short that window was. They didn't wait. No, they immediately filed for emergency observation time on the Very Large Telescope, the VLT, a facility run by the European Southern Observatory sitting at 2,600 meters elevation in the Atacama Desert of Chile, one of the driest and clearest places on Earth. The VLT is not a single telescope, it's 4 of them, each with an 8.2-meter mirror working in coordination. And on it sits an instrument called FORS, the focal reducer, and low dispersion spectrograph. It was built to do something specific and extraordinary, measure the polarization of light from distant objects. Polarization is the key to this entire story. Light is an electromagnetic wave. Normally, those waves vibrate in every possible direction, simultaneously up, down, diagonal, every angle. But certain physical conditions can cause light waves to preferentially vibrate in one direction over others. That's polarized light, and it carries information that unpolarized light cannot. Specifically, it carries information about shape. If you have a perfectly spherical explosion expanding in all directions equally, the light coming from every part of that sphere cancels out. No net polarization, 0. But if the explosion is not a perfect sphere, if it's elongated, stretched, asymmetric, the light from different parts of the explosion doesn't cancel. You get a measurable signal, a direction, a preferred axis. The degree and orientation of that polarization tells you precisely what shape the explosion is, and you can measure this from 23 million light years away, because light carries the information across the entire distance without losing it. Yang's team pointed FORS-2 at SN2024GGI and started collecting data. What they found was unambiguous. SN2024GGI was not a sphere. It was shaped like a prolate ellipsoid, the technical term for the shape of an olive, or a rugby ball, or an American football, stretched along a single axis of symmetry with the same elongated, organized geometry on both ends. This was not a chaotic mess expanding in random directions. It was not a turbulent, lumpy fireball. It was a clean, structured explosion with a dominant axis, like something had fired through the star along one direction and pushed the material preferentially outward along that line. That shape is a clue. And to understand why it matters, you need to understand the two main theories that have been competing to explain how supernovae actually work. The first is the neutrino-driven model. When the iron core collapses, it triggers a nuclear reaction so energetic that it produces a burst of neutrinos, subatomic particles with almost no mass, that travel at nearly the speed of light and almost never interact with ordinary matter. In 1 second, a collapsing stellar core emits more neutrinos than the sun will produce in its entire lifetime. Almost all of them pass straight through the star and escape into space. But almost is doing a lot of work in that sentence. A tiny fraction, maybe a few percent, get absorbed by the material just outside the core. And those absorbed neutrinos deposit energy. Enough energy, the theory proposes, to re-energize the stalled shockwave and push it outward to complete the explosion. This model has a lot going for it mathematically. It's been the dominant theory for decades, and in some 3D simulations it works, it triggers explosions. But the explosions it produces look a specific way. Neutrino-driven models tend to generate turbulent, irregular blasts. The shockwave gets driven by convective plumes bubbling up in the different directions. The resulting explosion is asymmetric in a disorganized way, lumpy, messy, with no single clean axis of symmetry. That is not what SN2024GGI looked like. The second theory is the jet-driven model. In this version, the collapse of the core generates powerful magnetic fields, and those fields channel material into narrow, focused jets that fire outward along the star's rotation axis, like the star is a gyroscope, and the explosion is blasting out through its poles. Jets would naturally produce exactly the kind of elongated, axially symmetric explosion that FORS-2 observed. If jets are punching through the star along one axis, the material gets flung out preferentially in that direction. You get a football shape, but jets have their own serious problems. When you run 3D simulations with realistic physics, jets are unstable. They don't stay focused. They wobble. They change direction. They can lose coherence entirely before they punch through the star's outer layers. In many simulations, jet-driven models fail to produce a full explosion at all the jets die out before they can finish the job. So you have one model that can trigger explosions but predicts the wrong shape, and another model that predicts the right shape but can't reliably trigger the explosion. Neither is complete. And SN 2024 GGI has just made the problem sharper. Unless, and this is where things get genuinely strange, both are partly right. There's a newer class of models that researchers have started taking seriously, built around the idea of what they call jittering jets. The concept is this: when the core collapses, it does briefly generate magnetic jets. But those jets are unstable from the start. They don't fire cleanly in one direction. They wobble, they twist, they point in slightly different directions in rapid succession. And as they jitter, they deposit energy erratically into the surrounding material, not in a clean, organized way, in a chaotic, violent way that churns the material near the core and builds pressure from multiple angles simultaneously. The jets fail. They don't survive long enough to punch through the star, but they've already done the work. They've re-energized the stalled shockwave, given it the kick it needed to restart. The inner mechanism is chaos, but the outer explosion still carries the memory of the star's original rotation axis. because even jittering jets jitter around a central direction, and that direction, the rotation axis of the star, imprints itself on the overall geometry of the blast. What you're left with is an explosion that looks organized from the outside, clean, elongated, symmetric, but was driven by something turbulent and irregular on the inside. That is a near-perfect description of what SN 2024 GGI looked like. Not clean enough to be a simple jet, not chaotic enough to be pure neutrino turbulence. Something in between, something that may require us to build an entirely new generation of models that can contain both. Here's what this means beyond the physics. Every atom of iron in your blood was forged inside a star that exploded billions of years ago. The calcium in your bones, the oxygen in your lungs, the silicon in the rock under your feet, all of it was synthesized inside stellar cores and scattered across space by supernovae. You are, in the most literal and chemical sense, the debris of dead stars. And we have never fully understood how those deaths actually happened. We've had the broad picture for decades, but the mechanism, the precise sequence of physics that turns a collapsing core into an explosion that seeds an entire galaxy with elements has remained genuinely, stubbornly unsolved. SENN 2024. GGI is one data point, a single observation taken in a narrow window that almost no supernova has ever been caught in before. It cannot, on its own, resolve a debate that has occupied some of the sharpest minds in astrophysics for 30 years. But it has done something invaluable. It has shown us that the geometry of the explosion is real, measurable, and structured. It has given the competing models a new constraint they have to satisfy, and it has demonstrated that catching supernovae in their earliest hours is not just possible, it is enormously, irreplaceably, scientifically valuable. The Vera Rubin Observatory, scheduled to begin full operations soon, Idigan will scan the southern sky with a camera so large and so fast that it will detect orders of magnitude more transient events than any previous survey. It will catch more supernovae earlier, in more galaxies, at more stages of their evolution. Each one is a new data point. Each one is another chance to test whether SN2024GGI was typical or whether it was an exception. Another chance to measure polarization, to read shape, to trace the fingerprint of whatever mechanism drove the explosion. The universe has been exploding massive stars since the first generation of them formed, nearly 14 billion years ago. Every explosion has scattered the building blocks of everything that came after. We are finally starting to understand how it was done. If this video made you think differently about something you thought you already understood, share it. The people in your life who'd find this fascinating probably don't know it exists. Send it to them.